This is Unit 8, Video 14. In this unit, or this video, we will talk about the technique of titration. Very important lab technique associated usually with acids and bases, but this technique can actually be used for many reactions, as you'll see. So this is a technique, a lab technique, used to find the concentration of an unknown, say an acid, from a known, say a base. And you can reverse it. So usually what you have is you have the use of something called a burette. A burette is an instrument that is graduated. It has numbers. This is 15, 16, and so forth. Actually, the 16 would be down here. It's graduated from top to bottom. The top numbers are smaller, the bottom numbers are bigger. And it allows you to measure exactly how much liquid is coming out. In this case, if you put a base in there, you put your known in the burette, and then your unknown goes in the flask below. In this case, the acid is unknown. And you do a little titration, and you'll use an indicator to indicate for you when the reaction is over. And then you can calculate the concentration of your acid from your base and vice versa. So we'll do a few example problems to show you. A few definitions. First, the equivalence point of a titration is the point at which all the acid will be neutralized by all the base. So where the two are equivalent. And this is determined stoichiometrically. So this is like the theoretical yield that we talked about in stoichiometry. And it's important to understand that at the equivalence point, the moles of the acid equal the moles of the base. The 2 moles equal at the equivalence point. That's why it's called the equivalence point. Usually, practically, an indicator is used to see this happen in the laboratory. And phenolphthalein that we've talked about, which goes clear in acid to purple in base, is usually the indicator of choice. It's easy to see the difference in the color, really sharp difference, and easy to work with, and it's safe. Now the other definition is called the endpoint. The endpoint is the point at which all the acid has been neutralized by all the base. And this is determined experimentally in the laboratory. Now the only difference, these definitions essentially sound the same, except this one, the equivalence point says will be, and the endpoint says has been. So this is stoichiometric equivalence point. This is like the theoretical yield, and the endpoint is like your actual yield, the actual thing that happens. The two should be the same. You're hoping that your endpoint, the point at which you end your titration, end your reaction, corresponds to the equivalence point, what it should have been. That's the hope, and most reactions are set up to make sure that does happen. Alright, we're going to do a few example problems and go from there. How much 0.80 molar sodium hydroxide solution should be added to 25 mils of a 0.45 molar HCl solution to reach the equivalence point? So the equivalence point is the point at which the two are equal. So what we will do, we have ourselves an acid versus a base. Now we're given 25 mils of 0.45 molar hydrochloric acid. That's how much we have. And we're asked for how much of the base should we add. Well, because they're equivalent in terms of moles, the moles are equal. Let's find out how many moles we have of our acid. So this is through molarity. Remember, molarity is moles over liters. So if we want to find moles, we simply multiply molarity by liters. In this case, my liters is 25 mils. So I got myself the moles of acid. We'll say for the acid, here's what we've got. We've got moles equals, our molarity is 0.45 times 0.025 for our liters. Now, if you multiply these two, you should get yourself 0.01125. This is now moles of acid. Now, I can go ahead and put HCl here. We'll say moles of HCl, which equals the moles of base. So for my base, because we're equal, we'll say this equals 0.01125 moles of my base, in this case sodium hydroxide. Now, you do have to watch out to make sure that the stoichiometry between the two is 1-to-1, and in this case it is. Hydrochloric acid plus sodium hydroxide is a 1-to-1 stoichiometry. If you balance the equation, you'll see it'll be balanced as it is. And the most important thing, it's 1 HCl for 1 NaOH. Now you know that because there's 1 hydrogen in your acid, there's one hydroxide in your base, so you know you don't have to do any multiplication by 2 or divide by 2. But say if this was a diprotic acid, say if it were sulfuric acid, well, you know you have 2 hydrogens, so you have to consider the stoichiometry. In other words, your hydrogen may be twice as much, and so forth. Alright, so the base now, we want to solve for how much, and how much means in terms of milliliters. So we're actually going to solve for liters. In this case, liters, if you rearrange this equation, we're just swapping these two. Liters is moles over molarity. So in this case, our moles was determined to be the same as the moles of acid, 0.01125, divided by molarity, which is 0.80, and this gives us, let's go ahead and divide those numbers, 0.014. Sig fig wise, we get 2 sig figs. Now this is liters, because this was moles, and this was moles per liter. So the moles cancel out, you get yourself liters, which in milliliters is 14 milliliters. And this is our final answer. So what this means is that it takes 14 milliliters of this molarity, sodium hydroxide, to cancel out, to neutralize 25 milliliters of this molarity, hydrochloric acid. Now what you'll notice is that the hydrochloric acid is less concentrated, 0.45, versus the sodium hydroxide, which is more concentrated. So it would make sense that it takes less of the sodium hydroxide, less than 25 mils, in other words 14 mils, to neutralize all the acid. So you can step back and check if the stoichiometry makes sense. Let's try another one that's a little more involved. In a titration experiment, it takes 35 mils of 0.10 molar sodium hydroxide solution to neutralize 42 mils of HCl. What is the acid concentration? This is actually the standard titration problem, where you're trying to determine the concentration of your substance, of your acid in this case. And we'll do it the same way. It took 35 mils of 0.10 molar sodium hydroxide. We're going to go to moles again. It's all about the moles, which comes from molarity. So again, moles is molarity times liters. So we'll have to use molarity, 0.10 times the liters, the 35 liters, to find the moles. So this will be for our base. So in our base, the moles will equal our molarity, which is 0.10, times our liters, which is 0.035. We just moves the decimal place left once, so we get 0.0035 liters. Whoops. Moles of our base. In this case, sodium hydroxide. Now, we're going against hydrochloric again, which is a 1-to-1 mole ratio. So we know that our acid will be 0.0035 moles of HCl. This is at the equivalence point, again, because of the equivalence point. And we're asking what's the concentration of the acid. Well, we know that for the acid, the molarity, that's what the concentration is. It's the molarity that we're solving for, is moles over liters. Our moles is 0.0035, and our liters looks like is 42 mils, which is 0.042 liters, and that gets us, we divide those two numbers, 0.335, we get 2 sig figs, so 0.33 molar hydrochloric acid. Now, analyzing this, it looks like the acid, let's try that again, that looks a bit suspicious. Well, that sounds about right. So 35 mils, no, so we went wrong somewhere. Since I know that if it takes 35 mils of 0.10 molar to get rid of 42 mils, my acid concentration should be less concentrated, and it should be not 0.33 but 0.033. Let's see. Since we went wrong, this is a good way way to analyze our concept, if you take a look at what I'm talking about, is that if my acid is 0.33 molar, which is quite a bit more concentrated than the base, then it should have taken more base to neutralize it, not less. But 35 mils is not much. So we have 35 mils, 0.035 times 0.010, 0035, that's the moles, and 0035 over 0.042 liters of the acid should give us a little pause. Aha! It's the calculator has failed us. This number is 0.083 molarity. That's much better. Here we go. So logically, looking at it, stepping back and double checking is wise. In other words, now this makes sense. So because our concentration of the acid is less, well, then it should take less of the base to neutralize it. Now it makes sense. Excellent. Glad we found the calculation error, and that's it, 0.083 molar. So the last problem here that we'll do is, during a titration experiment, 50 mils of 0.16 molar hydrochloric acid was being titrated with a 0.20 molar sodium hydroxide solution. Once the pH after 15 mil has been added. For this one, I haven't done this in the previous problems, but let's go ahead and draw the picture of the experiment itself, since we're going to be doing a few of these experiments, hopefully. So here's your burette containing your base. In this case, this is our NaOH. And it's actually telling us that this is 0.20 molar NaOH. Right down below, in our flask, is our acid. So here's a finely drawn flask, and our acid will make it red. Here is, looks like we've got 50 mils of 0.16 molar HCl in here. So what we're saying is we're about to add a bunch of base to it. Now as the base gets added to it, it neutralizes it, causing the pH to go up. The beginning pH of this acid can actually be determined by simply negative logging this number. If you negative log this number, you get yourself a pH that's actually close to 1, essentially. Actually 0 point something, probably 0.8 or something. So this is pretty low pH. And as we're adding the base, the pH will slowly go up because the base is neutralizing the acid. Now, at the equivalence point, when we neutralize all the acid, so at the equivalence point, the pH will actually be 0. Did I say 0? It'd be 7. The pH will be 7 at the equivalence point. And before then, it'll be acidic, and then after then, it'll be basic, if we keep adding sodium hydroxide. So the trick here is we're actually going to add only 15 milliliters of the base, and to neutralize all of it, we'd have to add quite a bit more. So we're not going to be at the equivalence point. So we're going to be somewhere below the equivalence point, if that makes sense. So this is actually the one that's the difficult one, the one that's a little more involved. So see if you can follow along. The first thing I need to find out is how many moles of my acid do I have in here. I want to know the moles. How many moles of the acid is in there? And then, when I add 15 mils of the base, I'll be able to find out, well, how many moles of the acid have I neutralized, have I titrated, and then how many moles do I have left over? And that's the idea. So let's find out the moles. Again, moles is molarity times liters. So for my base, or rather for my acid, in this case I'm actually going to be doing my acid. So the reason I'm doing the acid is because the 50 mil and the 0.16 molar is for the acid. So I will do, the molarity would be 0.16 times 0.050, and that should give me 0.16 times 0.05, 008. Now this is moles of HCl that I have to begin with. So in here, you can actually say there's 0.008 moles of my HCl. So now we know how many moles are in there. Well, let's see. If we're adding 15 mils of the base, that's 0.20 molar, well, how many moles of the base have we added? Let's do the same thing for the base. So now we've got ourselves, so for the base, we can do the same thing. We got 0.20 times 0.015. Let's see how many moles of the base I've added. So 0.2 times 0.015. Looks like I added 0.003 moles of the base. In this case, standard sodium hydroxide. So you'll notice that I am not at the equivalence point. The big idea here is you have not neutralized all the acid. To neutralize all the acid, I should have added 0.008 moles. Notice I only neutralized about a third, a little more than a third of the acid. So how much acid do I have left over? So acid left over. What I have is I have 0.008 minus 0.003, and I got myself 0.005 moles of acid left in here. So as the titration goes on, what happens is a little bit of it gets neutralized. We'll make it green. So now this gets neutralized by the base, by the added base, and then the rest of it is still acidic. Now what I need to know, well, what's the pH now of the acid that's left? Well, to get the pH, I would need to negative log the concentration of the acid that's left. And the concentration has to be in molarity. So I have to solve for molarity of the acid. Now I've got molarity as moles over liters. So I've got my moles. Here's my moles, 0.00 moles. But how many liters do I have? Do I still have 15 milliliters of the acid? Well, not really. I have more because I've added 15 milliliters of the base. I actually have a total volume of 65 milliliters. That's now the total volume. What happened is this actually went up in volume as you added the base. So you actually have 65 milliliters. So my molarity then would be 0.005 moles over 0.065 to get my molarity there. So if you divide 0.005 by 0.065, you get yourself actually 0.0769 for the molarity of the acid. Now it says what's the pH of the solution. So to get the pH, we simply negative log that. So if we get the pH, that would be negative log of 0.0769, and that will equal, we're almost there, we'll have to negative log this. .1 for the pH. So we got two figs, so 1.1 is the final answer. So it took a little bit to get here, but see if you can analyze the problem with fresh eyes. Now the pH actually went up a little bit. So my original was not 0.16, it was probably 0.09. No, I'm sorry, it was 0.16. The concentration, the pH, this was the concentration. Concentration was 0.16. The pH was probably 0.09 or something. So the pH should have gone up. What I'm saying is that we started with a more acidic solution. As we added the base to it, it became less acidic. The pH went up. This is a little more involved. We'll practice a lot of this in class, and then we'll do a little lab corresponding to the same thing. All right, we will see you then.